All right, so for those of you who are just entering in and watching the video, my warning for you is that this person we're watching the video on today, his shtick is to use current affairs and look at the data and the stats behind them. There is zero political agenda to this. There is no intention of proving one point or another. It is purely my intention to look at this data and use this video as a teaching opportunity for how to do a chi-square test. There is no any other intention behind it. So please watch it with open ears and with knowledge that there is no ulterior motive to us watching this video. Okay, so chi-squared test. And again, I will interject as we go through this. So have your calculators out.
Chi-square test for dependence. Question is there convincing evidence of an association between race of suspect and level of force used? We see differing rates in the sample. The question is, are those different rates different enough to suggest that in the whole population, all people stopped during this program, there was meaningful differences in the level of force used between racial groups? Or if not meaningful differences that couldn't have arisen by chance alone. So we're going to do a significance test for this. We need convincing evidence of it. So the initial idea of what I have is to compare proportions using two sample z-tests. And you can compare proportions, say, for Black and Hispanic, they receive no force, they receive hand level of force, they receive a higher level of force than for Black and white, et cetera, et cetera. If you want to compare all these proportions, you can end up doing a hypothesis test. But it's not a good idea. One, it's just a lot of work to do. And two, you might get a type 1 error because of the problem with the test. You always have some chance of getting a type 1 error where you find a statistically significant result by chance alone. And if you keep on doing tests over and over again, you're bound to trip up and find an error. So instead, let's do one overall test. This is the chi-square test for independence. Here are the hypotheses. The null is going to be that there's no association between racist suspects and level of force used. The alternative is going to believe there is an association between those variables. In this case, it fits into our innocent until proven guilty framework. The null is going to be that force is used at the same rate between all racial groups. And the alternative that we need proof for is that the force is going to use at different rates between racial groups. So let's go through the logic hypothesis. Like always, we start by assuming the null is true. So we're going to assume that force is used at the exact same rate between each racial group in the population. And then we're going to say if.
So I'm going to pause right there. We did stuff like this on the first day of chi-square tests. So remember with chi-square tests, we are now looking at categorical data versus quantitative data. And one of your homework assignments said, or maybe it was in the notes, we talked about days of the week and our birth rates the same. So we went ahead on the assumption that the null was true and that each day of the week had the same number of births, and we had the proportion as 1/7. So that's what we did. Now we're kind of doing this again. The difference between section 11.1 and this test or this day, 11.1 only really had one variable, M&M color or birth rate. There was only really one variable, where today we're going to look at what we call a two-way table. There's multiple variables. In this particular first assignment, you've got the first variable is the amount of force, and the second variable is your race. So there's two variables attached to this. And again, what he said was we could compare two things, do a hypothesis or a significance test on two of them, but you'd end up, in order to do all the comparisons that you would need to compare, you'd need 9 tests. Nobody wants to do a state plan. You conclude 9 times in order to come up with one final solution. So again, this is your categorical. It is different compared to the chi-squared goodness of fit test because there is more than one variable that we're looking at. So keep that in mind.
This null is in fact true, how likely is our sample data that random sample data stops from coming? So we're going to compare the distribution of force levels across our sample and see how similar or different they are. And then we're going to draw a conclusion. If different enough, we have evidence that force levels are actually used in different rates between rich groups. We reject force is used equally across racial groups. So we're going to redo this data and think about the expected counts if there was an equal force rate used between each of these racial groups. So let's break down how we do that. The overall go force rate of the whole table is simply the total amount of suspects across all groups where no force was used, 2,484, divided by the total of the whole table, 3,004. That's a rate of 78.5%. So if we're assuming the null in a world where force levels of force are used equally across all racial groups, we should see in our data that about 78.5% of suspects from each racial group received no force. So to get these in terms of expected counts with our different sample size for each racial group, we can do a second multiplication. When you find 78.5% of 1,743 black suspects stop, that's 0.785 times 1,743, and that's about 1,368.
Now I'm going to pause again real quick. Remember, when we are trying to find this chi-squared data, it was your observed minus expected squared, all divided by the expected. And how we figured out the expected count was to take the probability of that happening multiplied by your sample size, n times p. So that's exactly what he did to get this 1368. Again, we went based off the null. So we said, if all of these race groups had the exact same amount, which is meaning there's no difference, we took the total who had no force out of the grand total. That was 78.5%. That's my proportion. We then have of the black race, there were 1743. That's my sample size. So 1743 times the proportion. That's where we have the expected count of 1368, the n times p in order to get expected. Because again, we're going to need observed minus expected squared all over expected.
68 black suspects to receive no force given how many stopped. And we do that for each racial group here. For Hispanic suspects, we get this number. For white suspects, we get this number. And if we want to have a simple formula to do this for all force levels of racial groups, here is a simple formula for finding those expected counts. We do the row total times the column total divided by the grand total. We essentially did that.
So I'm going to shorten it up a little bit. That's a lot of work to first find your probability, then multiply it by n. So what you guys can do is you can do your row total times your column total, all divided by the grand total. And that will get you each one of these numbers. So row total by column total divided by grand total. But I'll make it even easier later.
But this is just a formula we can use.
So in this case, we have.
I have to pause this here recording, guys.
For black suspects receiving no force, we look at the row total. The row total was 2,804. We look at the column total. There was a total of 1,745 stop divided by the grand table total, 3,164, and you get what we got for our expected count, 1,068. So we can do this for the stuff we haven't built in yet. For example, Hispanic suspects receiving a hands level of force, we can look at the row total times the column total divided by the grand total, at 1,169. We do that for all these different groups. So for example, black suspects receiving a very level of force, the row total, column total, and get those numbers. And if you do this for all of those spaces, we can get all of our expected counts. So in this world where force levels are used equally across racial groups, these are the expected counts we expect to get, given how many of the suspects from each race were stopped. So now we're going to take these expected counts and we're going to compare them to the actually observed data from our sample. So here is the actually observed data again. And we're going to look and see how those comparisons match. So white suspects, it looks like, receive force less frequently than expected based on Last suspects had force levels pretty close to what was expected. And this makes sense because black suspects made up stops from police, so they disproportionately define what is expected in the data set. And Hispanic suspects received force more frequently than expected and had no force interactions less frequently than expected. So now the question is, statistically, are these differences that we see overall large enough to say that it didn't happen by chance alone? So that's where our chi-squared test statistic comes in. Now recall the chi-squared test statistic. This is how it works. First, you look at the expected counts and the observed counts and you subtract them to find the difference between what was observed and expected for each table sample. Then we square those differences, add up all those differences together, there's no negatives to cancel things out. We divide by the expected counts to scale by what we expected. And then we add all of that up to get a sense of the total differences in this table. So if you want to see the precise derivation of this, you can go back to our last lesson on chi-squared groups for more detailed explanation. And we know that when chi-squared is big, that means the observed data is very different. Those differences are very large compared to what was expected under the hypothesis. In that case, your observations, your sample data was unlikely under the assumption that it was true. We got a low p-value to reject the null hypothesis. So when the chi-squared value is small, that means that your observed data was very similar to what you expected from the hypothesis. Those differences are small. Therefore, if your null is true, your observations are relatively likely. You're going to fail to predict the hypothesis. You don't have convincing evidence against it. So in this case, we had our expected counts and our observed data, and we're going to plug these into our formula for each cell in our table. Let's look at first black, no force. We plug in the observed, the expected counts. We have for Hispanic, no force as well, and we do a plus not done.
I'm going to pause right here. So as far as work on the AP test that they would expect you to do, because we are going to do all of this in your calculator, to be honest with you, you're not going to be doing any of this computation by hand. You're not even going to have to do the expected count computation by hand. We have our calculator and I will show you how to do all that. But here's what I want you guys to know. AP test will want you to actually write out this expected count chart. Again, we will get that from our calculator, but they will want you to show the first couple, and you see how they kind of ended it with ... Okay, they want to see that you know what numbers to put in there and making sure they know the right order. So again, it's observed minus expected squared all over expected. But then they know you don't have to write this out 9 times. If you can do this correctly twice, they know with certainty that you know how to do it. So please feel free to start your work, but then use the ... which implies, and this pattern would continue. So you will have to write out the expected counts. You will have to write out the beginning of your chi-squared, but the rest of it, they expect you to be using your calculator.
You hard to do all these by hand. We actually have calculator steps for this. I'm going to show you what you get in the meantime. If you did all this, you get 10.17 when you add everything all up. So is this big enough to reject the null? This chi-squared test is 10.7. Yes, it is. How do I know that? Well, I'm going to show you during our 4-step process. So let's go through the 4-step process. You're asked the question at part 2, this is the way to organize your work such that you get full credit. And so when you're asked, is there convincing evidence of association, I go through the 4-step process for inference and do a chi-squared test for independence here. So first, you want to state your hypothesis at significance level. We've written out hypotheses before, we state them, and we have an alpha level of 0.5 here. Plan, you want to name the inference method and check conditions.
So make sure you guys understand the name of the test. So you will have to do a chi-squared test for independence. Okay, that's this new one. That's what we do for 2-way tables, is a chi-squared test for independence. We'll review section 11.1 very quickly. You did a chi-squared goodness of fit test if it was only one variable. So chi-squared test for independence is a 2-way table.
I'm going to check my conditions. We have these 3 very familiar conditions for us. Random. The data was randomly sampled from 2011 stock first records, so we're good there. 10%. My sample size should be less than 10% of the population size. In this case, my sample size of 3,164 stops I'm looking at should be less than 10% of the whole population of all 2011 stop and frisk stops. And then
I'm gonna pause there again. Something I noticed on some of your guys' homework, when you were doing the 10%, you were looking at the individual categories. What I want you guys to see is that this is your grand total. If you rewind the video, that 3164 was the total. That was everybody in your sample, not the individual columns and not the individual rows. You only have to do one 10% condition, and that is based on the total people in your sample.
85,000 such stops in New York City that year. That's much less than 10%, so we'll get there. Large counts, all expected counts can be greater than 5. Well, it's very hard to get all the expected counts by hand. There's a lot you have to do. There's a good way to do it in your calculator.
All right, so this is where we're gonna practice in our calculator. Okay, what I want you guys to do in your calculator, so grab it out right now. I am going to pause. I'll do my best to do this right along with you in your calculator. But again, my TI calculator on my computer is a little bit different. So I'm going to stop screen sharing this. I'm going to screen share my iPad. So give me 1 second. Okay, so we need to actually enter this data in as a matrix, not a list. So your matrix button, if you hit your second button, your matrix is the 4th button down on the left-hand side. You'll see it's right above the x to the -1. Okay, what we need to do first is we need to go to the right because we need to be on the edit menu. And we are going to edit matrix A. How we do matrices, it's a rows by columns. So we had a 3 by 3 matrix. We had 3 rows, types of force, 3 columns. That was your race. And I will, hopefully you guys are with me. I will walk you through the data. We are going to put our observed data into this list, observed data into the list. So it was 1371. Type in 1371, press enter. Then it was 853. Enter. We had it 260. Enter. We had 263. Enter. 188. Enter. 30. Enter. 109. 72 and 18. And again, this is your observed counts. Once you have your matrix in there, what I want you guys to do is you will hit your stat button. And again, this is where you're going to have to verbally listen because this calculator does not have the option for me to show it to you. But you will go to your test. So test menu, so scroll to the right twice. I'll be honest with you, I usually push up because it's down at the bottom. And here's where I'm going to stop screen sharing this and go back to my computer because my computer has it on there. You are going to find the chi-squared test, not the chi-squared golf test, but the chi-squared test. It's right underneath the chi-squared golf. So we have our matrix in there. We enter the observed data. When you find in your stat, scroll over to test, we're doing the chi-squared test. This is option C. Your observed data is matrix A, and it says your expected is B. Leave it alone. Your calculator will automatically fill in matrix B. Go down to calculate, press enter, and you should all get this chi-squared number, yes? You get it, Erica? Yeah. Awesome. We also have the p-value. We will talk momentarily about this degree of freedom. Here's the next thing that I verbally want to tell you. Let's find our expected counts. I want you to go back to your matrix menu. So hit second x to the -1. Go back into matrix. Go down one, do not go over to edit, just be on that main one, go down to matrix B. So on your home screen, it should just say matrix B, press enter. You should get your expected counts matrix now. And we'll go over that again. So let's keep watching the video, but we'll practice this.
The steps that you can do, is you can try this out, take a pause in the video. The chi-square test will actually be computed by this, and so you can write down this output to save it for later for the do step, and then these last steps here get you the expected counts on the TI-84. So then once you do that, you write down the expected counts, and you say, yes, these are all there. Now for the do phase, in your report to degrees of freedom, as well as your test statistics. In two-way table analysis, degrees of freedom is going to be the number of rows in the table -1 times the number of columns in the table -1. When I say rows and columns, I don't mean the total columns, like totals for the rows, totals for the columns. No, I just mean for the variable values. So in this case, we have 3 columns and 3 rows, and 1 and 3 for each. Subtract before multiplying, because we're in parentheses, and then we get 2 times 2, which is 4. So we have 4 degrees of freedom, and the calculator gave us all the rest of the test statistic and the p-value. Now, in order to show my work, I'm going to write in a couple of the chi-squared terms, expected, mass observed, squared root expected, just to show that I know my work. But then I'm going to plus, dot, 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 and I'm going to write in what my calculator gives me, chi-squared of 10.7 with a p-value of 0.038. It's a small p-value. So let's conclude. We have our conclusions template here. And I'm going to say, because our p-value is 0.038, and that is lower than our alpha value of 0.5, we're going to reject the null hypothesis. We have convincing evidence that there is an association between the race of suspects that were stopped and the level of force used against them. So let's compare this really briefly to what we call a chi-square test for homogeneity.
All right, so I'm going to explain the difference there. Look at number 2. This was your chi-square test for independence. And number 4, the chi-square test for homogeneity. These seem and feel very similar. Your biggest difference between the chi-square test for independence and your chi-square test for homogeneity is how many sample groups did you have? In the example that we just did, all of our data was pulled from New York. So they had one sample and we looked at multiple variables within that one sample. The chi-square test for homogeneity, you're going to see it. Now they're going to pull from New York. They're going to pull from Boston. They're going to pull from, I forget what the third city was, 3 different sample groups. And they're still going to look at one other variable. So we have more than one sample group. Independence has one sample group. And we looked at multiple variables in there. Homogeneity, multiple sample groups. Keep watching.
Chi-square test for homogeneity is the exact same thing. It's the same thing as a chi-square test for dependence. There's only 2 key differences. The data is set up a little bit differently, and the hypotheses are going to be a little bit different phrasing. So what we just did is an independent situation. Here's the data set. There are 2 variables, in this case, race of suspect or sample, and they're sampled from one population, stops in New York City. And so these were my hypotheses. Variable 1 is not associated with variable 2, or they are. This is what was context. In a homogeneity situation, the data sets are going to be different. Imagine we did a different study, which we're testing the association between the race of suspects stopped in different cities. So, for example, here we have one variable, which is the race of the suspects that police stopped in different cities from multiple different samples from multiple different populations. So we have a sample from New York City, a sample from Boston, and a sample from LA. So this is one variable, the race of the suspects, in 3 different contexts and 3 different samples. So this is one variable, multiple samples. This is a homogeneity situation, not an independent situation, homogeneity. The way we write the null alternative hypothesis here is that there's no difference in distribution of that variable between groups 1, 2, and 3 samples, and there is a difference in the alternative. In this case, that would be there's no difference in the true racial distribution of stops in New York City, Boston, or LA. Or alternatively, there is a difference in the true racial distribution of stops in New York City, Boston, or LA. So these tests are very similar. They both deal with 2-way tables. We have the same conditions, math, procedures, etc. So the statement would be very similar. The only difference is the data is set up differently, and we have a differently phrased hypothesis, and therefore a differently phrased conclusion. If you reject or fail to reject. So,
all right. that is done with the video part. So at this point, again, I'm going to go back to my iPad. I want you guys to get the 11.2 notes from Schoology if you haven't done so already. Okay, so get your 11.2 notes. I'm going to screen share on my iPad. And we're going to go through the notes. This is where hopefully you guys were listening, you are absorbing in the video, and now we're going to put some stuff on paper so you guys can practice this. So 11.2 notes from Schoology. There we go. So 11.2, what we are going to do over here, I have some stuff highlighted and I have some, I highlighted it, but in your notes are already pre-underlined. Homogeneity, what I want you guys to see on this third check mark, if you are doing homogeneity, homogeneity is one categorical variable amongst different or multiple populations. Okay, so multiple populations, multiple sample groups. So homogeneity, multiple sample groups. Where the chi-square test for association, that was the first one, it was one population, but you're looking at two categorical variables. Two variables, one population is chi-square test for independence. Chi-square test for homogeneity is one variable, multiple populations. Okay, so please understand the difference because the setup is going to feel very similar for them. Okay, so as we look through, again, I kind of have this in the table. We had the same table in our 11.1 notes. If you have one categorical variable, that's it. One population, one categorical variable, that's your chi-squared goodness of fit. Homogeneity is two categorical variables. But no, homogeneity is going to be one categorical variable, multiple populations. Two categorical variables, one population is going to be your chi-squared test for association. So this data that we looked at, because if I haven't been winning already with the data that we've talked about today and race and police force, let's talk about, does music affect which wine you purchase or which wine you purchase? So I'm clearly winning for both of these things today, but it's data, we're just looking at the data, okay? So same idea, what this one was, is we are trying to decide if the type of music that a business plays affects the type of wine that somebody purchased. So again, what I want you guys to see when we're talking about degree of freedom, we looked at the number of rows compared to the number of columns. And for the degree of freedom, we took the number of rows minus 1 multiplied by the number of columns minus 1, rows, columns, and we get out, in this case, this would be, again, a degree of freedom of 4. Why do we need degree of freedom? Because we are looking at the chi-squared test, which is similar to, well, yes, chi-squared tests require a degree of freedom. So we're trying to, again, find out if there is an association. We know this is an association, not a homogeneity, because we're only looking at one sample population. We're not looking at multiple different sample populations. And we're comparing music group to wine purchase. So there's two categories, one population. So things that we talked about, we are looking at, is there a relationship or an association between music and wine purchase? So we'll kind of talk this through again. I'm going to go through this fast because a lot of this is the same thing as what we talked about in the video. And again, are the distributions different? We would expect that music would not have an effect on it. We would expect that your percentages would be the same across all of the types of wine purchased, regardless of what music was being played. So just kind of looking through the data here, percents of French wine sold versus Italian wine versus other wine when there was no music played. This is your percents again of the various types of wine when there was French music and Italian music. So if you're looking at this with percentages, that would be what your bar graph would look like. Doing our state plan to conclude, here's your state. There is no difference in the distribution. There is a difference. And part of your state plan to conclude is also to talk about your significance level. So you would want to put your hypothesis in there, and we also want to say an alpha level of 0.05. So make sure you write down what alpha level that you're adding. But again, it's all about no difference or there is a difference. So how we find the expected counts by hand, which you're never going to have to do. Remember, expected count is all about your row total times your column total multiplied by your table total. But I will never expect you to do this by hand. This will always be done in your calculator. So what we need to do is you guys need to stick your observed counts into your calculator. So this would be your 3x3 matrix in your calculator. This is your matrix A. We want this one to be your observed counts in matrix A. And again, I'm going to fly through this. But after, so know that you can get this information from your calculator after you compute option C, which is the chi-squared test. Matrix B will show the expected counts. You have to actually do the chi-squared test in your calculator in order for it to show the expected counts. Okay, but again, AP will want to see your expected counts because that's part of your state plan to conclude. You would say, yes, all expected counts are above or equal to 5. So you would have to actually write this matrix down. That's part of your checking conditions. But again, that comes from your calculator work. You're not going to be expected to do this by hand. Same thing with actually coming up with your chi-squared test. Y5 prints, that's just your large counts condition, that your n times p has to be larger than 5, that your each expected count has to be larger than 5. Kind of like when we were doing all of our other tests from chapters 7 through 10, you'd have to check, is it normal? And you would do that if it was a proportion by doing n times p has to be greater than or equal to 10. Well, in a chi-squared test, making sure that our data is large enough, our expected counts have to be larger than 5. So again, AP would want to see the beginnings of your work, but you do not have to do all of this. Stop at your ... Let your calculator give you your chi-squared test or your chi-squared statistic. So I have all of that in there. Again, you want to go to your matrix menu, second inverse, X inverse, scroll over to edit, put your observed data in there. And again, after you compute the chi-squared test, your expected values will show up in your matrix B. You can either enter it in on your home screen or go back into edit matrix B and they'll be in there for you. Okay, so from there, again, after you compute your chi-squared test, this is C. Reminding you, the chi-squared Goff test is when there's one category. Chi-squared test is when there are 2 or more categories. It will give you the chi-squared, it will give you the p-value, and that fill in the blank. Because our p-value is less than our alpha level of 0.05, we reject the null. We do have convincing evidence of our alternate that there is a difference between the distributions of wine purchase and music played. So kind of the same idea, always put that alternate in context. Over here, again, degree of freedom, we kind of wrote that down already. You will not have to look at to find your p-value. You will not look at the table. Row -1, category -1. I wrote that down for you guys already. The only other thing that I really want to talk about is if AP gives you a computer output. This is not something that you guys would actually have to come up with, but AP may give you this computer output. So I did highlight the expected counts are in yellow. Observed counts are in pink. I missed a pink. And chi-squared contributions, the chi-squared test, remember, gave us a chi-squared number of 18.1. So each portion, each relationship kind of gives you their part that they added in there. And biggest thing that I want you guys to see, if you looked at these two in the red boxes, they have a large p-value contribution or chi-squared contribution. So you can say there are definitely relationships between Italian wine and French music, and Italian wine and Italian music. There's definitely a strong association between somebody buying Italian wine and French and Italian music being played. So that would be something that AP would give you the computer output on it, and you would just have to come up with the conclusion that's not something you would ever do. So I'm going to quickly go through this homogeneity again. This would be multiple populations, one variable, but you're going to do very similar things. You're going to put your information in a matrix. You will not use the totals. Do not include the totals. These are your totals. These totals, this one and this one, totals don't go in the matrix. Okay, your totals do not go in the matrix. Alpha level 0.05. Again, AP will want to see this after you do your chi-square test. Find your matrix B, which is your expected counts. These are the expected. AP will want to see this again as part of your large counts condition. And the rest of it, kind of the exact same thing. Look for that p-value. In this case, because the p-value is 0.2, which is greater than our alpha level, we failed to reject the null. There is not enough evidence to conclude that your alternate, that there is a difference in party affiliation between cell phone and landline only. And you can read the context of those questions. If you needed to see another worked out example, that is this last example in your notes. Actually, I think there are 2 more examples if you needed to see more written out. So that's all I have. That's the biggest difference between first lesson, last lesson is how many variables you're looking at. All of it's done in your calculator. You still need your state plan to conclude. Your homework is in class kick.